Chapter 8 talks more about bonding in molecules, covalent bonding specifically. So we have some theories to try to explain what we see in covalent molecules. So the first theory we're going to talk about is valence bond theory. And the covalent bond is said to form from overlapping orbitals. So let's take a look at the hydrogen molecule. The electron configuration of a hydrogen molecule is 1s1. It only has one electron and it's in the 1s orbital. The shape of an s orbital, if you remember those pictures of probability clouds, is a sphere. So we have a hydrogen atom with the orbital, the 1s orbital, looking like this. And then if we have another hydrogen atom with a spherical orbital, these can be put together and overlap. And so the two electrons that are both in these probability clouds can use this overlapping space to hop from one orbital to the other. And so both electrons are going around both of the nuclei. So here we have the hydrogen-hydrogen bond. Let's take a look at an HF molecule. So H still has that 1s1, so it has an electron that's in an s orbital. Fluorine has 1s2, 2s2, 2p5. So the electron that is unpaired and needs to form a bond is actually in a p orbital. And p orbitals do not look spherical. They kind of look like a double lobed shape. So here's the nucleus in the middle, so they almost look like a figure 8. And there's three different ones. That's why there's 3 boxes. So there's ones that go up and down, there's ones that go side to side, and there's one that go in and out of the page. So let's go ahead and take the one that goes side to side. So here we have some overlap between the p orbital of fluorine and the s orbital of the hydrogen. So again, this is like an overlapping space, and the electrons that are in this space can be shared between the hydrogen and the fluorine. A couple other features of this theory is that orbitals that overlap more, I should have said, form a stronger bond. So the orbitals that overlap more are going to form a stronger bond than those that overlap less. So sometimes you have a molecule where your textbook shows that maybe there's kind of a tilt to the way 2 atoms are arranged, and so you have 2 atoms that are trying to overlap their p orbitals, and the space that overlaps is very small. That's going to be a weaker bond than something that can overlap a bit more, like maybe this one. Also, we've already seen in our bond energies from chapter 7 that when you form a bond, that releases energy, and when you break a bond, that requires energy. So when we were looking at the enthalpies of reactions, we were adding in the bond energy of the bonds that need to be broken, and then we were subtracting the energy from the bonds that need to be formed, because we're kind of getting that energy back. We're releasing that energy when we form some bonds, but we have to put in the energy when we break the bonds. And there is a most stable length of a bond, so there's a bond distance, and that is the length that the bond has, the distance between the nuclei when the overlap of the orbitals is the most stable. Alright, so another thing we want to look at is the difference between a sigma bond and a pi bond. These are 2 types of bond overlap that can form. I encourage you to look at your textbook. They have some pretty good drawings there. I'll do my best with these drawings. Here is a diagram of 2 s orbitals overlapping. So here's the overlapping part over here. This is where the orbitals overlap. And if you draw a line from the nucleus of one atom to the nucleus of the other, it crosses that overlapping part. So that is a characteristic of a sigma bond. So remember, this p orbital is not a sphere, it is two lobes. So here's one atom that has a p orbital around it. Here's another atom with a p orbital around it. We have these p orbitals overlapping end to end. I've colored in the overlapping part, and if I draw a line from the nucleus of one atom to the nucleus of the other, I cross right through that part. Here's a drawing of an s orbital overlapping with another atom's p orbital, kind of like we saw before for hydrogen fluoride. And when we draw a line from the nucleus to the other nucleus, we cross right over this overlapping part. A pi bond, in contrast, is a bond where a line passing from one nucleus to the other does not cross over the overlapping sections. So here's an example of two p orbitals. Instead of lining up end to end like these, they're lining up side by side. So we have two atoms and the p orbitals are kind of siding up next to each other, and there's a little bit of overlap area here and overlap area there, but those areas are above and below the line that would connect those two nuclei. And so the line going from one nucleus to the other does not cross either of those overlapping sections. It crosses a node or a space in the middle where no electrons are supposed to be found. There's like a 0 probability of finding electrons there. When you are forming bonds between atoms, the first bond that forms will be a sigma bond. So if you have a single bond, let's say a carbon-carbon single bond, this is going to be a sigma bond. Here's a little Greek sigma. If you have a double bond, then one of them is going to be sigma and the other is going to be a pi bond. If you have a triple bond, one of them is going to be sigma and the other two are a pi bonds. So these two are both pi bonds. So each one of these scenarios has only one sigma and the rest of them, if there are any others, being pi bonds. Let's use that information to count the sigma and pi bonds in this molecule. So this information here, that the first bond that forms will be a sigma bond and the additional bonds are the ones that are going to be pi bonds. So I went ahead and colored the second bond of this double bond green and the second and third of this triple bond green. So these are the pi bonds. There's going to be 3 pi bonds, and all the ones that I did not color are going to be sigma bonds. And so I come up with 11 sigma bonds. So we had hinted at this before, but when we were talking about resonance structures, we mentioned that we could tell that the bond between two atoms was not just a single bond and not just a double bond, that it was in between. And the reason we can tell the difference is because there is a difference between a single bond and a double bond. First of all, the length of a double bond is shorter than a single bond, and then the triple bond is shorter still. And the energy that it takes to break the bond also increases, going from single to double to triple. So as these carbons form additional bonds, they're getting pulled closer together, and the strength of the bond between them is stronger. It takes more energy to break. So let's go ahead and fill this in. What do we notice about the distance between the double bond and triple bond carbons? They're getting closer when you have more bonds. So now we want to know the difference in energy between a single bond and a double bond. So if we take the difference between those two numbers, we can see that the second bond adds an additional 267 kilojoules per mole. So having a double bond is 267 kilojoules per mole stronger than having just a single bond. All right, and then the third question is trying to draw our attention to something about the strength of a pi bond compared to a sigma bond. So this first bond, the carbon-carbon single bond, is 347 kilojoules per mole. Then the second bond that forms, I've drawn the pi bonds in green. This burgundy color is the sigma bond. So this second bond is less energetic. It's 267 kilojoules, not 347. And then the third bond that forms is slightly less energetic still. So these new pi bonds that have formed are less energetic. They're weaker. It takes less energy to break them than the original sigma bond that was between the two carbons. So they are not as strong. So the pi bonds in this triple bond are not as strong as the sigma bond between the carbons.